What if I told you that the greatest snipers in history lived 2,000 years before the invention of the optical sight? We are accustomed to thinking that high-precision shooting is an achievement of modern technology, computers, and laser rangefinders. However, Roman legionnaires possessed weapons capable of hitting a single target at a distance equal to the flight range of a modern bullet. Their engineering genius transformed wood and animal sinews into mechanisms that did not simply throw stones, but hit the bullseye. The Roman war machine worked like a perfectly tuned clockwork mechanism, where mathematics killed more effectively than the sword. It was not the brute force of barbarians, but the triumph of science, geometry, and standardization over the chaos of battle. Every detail of their siege weapons was the result of centuries of calculations and bloody experience. They knew how to calculate trajectories that European scientists would only rediscover 1,500 years later. Their artillery was so advanced that it could target individual commanders on the ramparts and eliminate them with a single shot. This story is not about catapults, but about the world's first high-precision artillery systems. Watch the video to the end, and you will learn how Roman engineers used human hair to create energy capable of piercing iron armor. Are you ready to learn the truth about the most terrifying weapon of antiquity, feared more than an entire army? We are talking about the Scorpion, a light crossbow that changed the rules of warfare forever. This device was not intended to destroy walls or gates. Its target was living people. Imagine a huge crossbow mounted on a stand, operated by two specially trained legionnaires. The Scorpion struck with such force that its bolt could pierce through two fully armored soldiers, standing one behind the other. The sound of its shot was sharp and dry, like the crack of a whip, and this sound struck terror into the hearts of Rome's enemies. The main secret of this weapon was its incredible rate of fire for that time. An experienced crew could fire 3 or 4 aimed shots per minute, creating dense barrage fire. At a distance of 300 meters, the spread of hits was only a few dozen centimeters. Legionnaires used Scorpions to eliminate enemy officers and standard bearers before hand-to-hand combat began. This threw the enemy into chaos, depriving them of their command long before they could strike back. The Romans understood perfectly well that an army without commanders becomes an uncontrollable mob. The design of the machine was ingeniously simple and reliable, allowing it to be used in all weather conditions. All key components were protected by metal plates so that enemy arrows or fire could not damage the mechanism. The compactness of the Scorpion allowed it to quickly change position and support the infantry attack with fire from the flanks. Each legion had about 60 such machines at its disposal, creating an impenetrable wall of flying death. During a massive barrage, the air was literally black, with hundreds of heavy bolts flying at incredible speeds. It was virtually impossible to survive such fire in open terrain. The psychological effect of using Scorpions was no less important than the physical damage. Seeing their comrades fall dead from an invisible threat, the barbarians often lost the will to resist. The Romans methodically and cold-bloodedly shot the enemy, remaining out of range of their bows. The accuracy was such that there are historical records of hits to specific parts of the body from enormous distances. It was the sniper weapon of the ancient world, unmatched by any other civilization of the time. No armor of that era could guarantee protection from a direct hit by a bolt from a Scorpion. It was this weapon that allowed the Romans to keep their numerically superior enemies at bay. It turned the defense of a camp or fortress into the methodical and safe extermination of attackers. The Scorpion became a symbol of the technological superiority of Roman civilization over the barbarian world. What do you think? Was the use of such a long-range weapon fair to opponents armed only with swords and spears? Share your opinion in the comments, because the ethical question of war is relevant at all times. Want to know a secret that will change your perception of the energy sources of the past? The power of Roman artillery was not based on the flexibility of the bow, as in a conventional bow, but on the force of torsion, which engineers turned into a highly accurate and incredibly powerful mechanism. The Romans did not simply use the torsion principle. They perfected it, creating machines resembling huge springs capable of storing energy as reliably as modern steel coils. This was the secret of their formidable firepower. The mechanism was based on two tightly packed vertical bundles of ropes clamped inside a sturdy wooden frame. These bundles were the heart of the entire structure. It was in them that energy was stored, which was then converted into a destructive impulse. Powerful levers were inserted into each bundle, and a bowstring or rocker arm was attached to the ends of the levers, depending on whether it was a ballista, a scorpion, or a larger throwing machine. When the levers were pulled back, the ropes twisted like a clock wound to the limit, and enormous potential energy appeared inside them. The material for these ropes was selected with the same care with which alloys are selected for aviation today. These were not simple ropes, but specially prepared bundles of animal sinews, most often from oxen or deer. Roman engineers discovered that the tendons of the cervical spine had the ideal combination of strength and soft elasticity. Cleaning, drying, sorting by thickness, and subsequent processing became a real industrial chain stretching across the empire, from Gaul to Syria. But human hair, especially long women's hair, was considered the most valuable material. It had a unique combination of strength, flexibility, and durability that surpassed even the best animal sinews. Ancient sources mention cases when women from besieged cities brought their braids to blacksmiths and engineers, realizing that the fate of their families and cities depended on the strength of these strands. Such offerings literally became a contribution to the defense, turning into weapons that could pierce shields and break through walls. The secret to the effectiveness of the torsion bar lay in its perfect symmetry. Both bundles had to be twisted with exactly the same force. Otherwise, the blow would be skewed and the projectile would veer off course. For precise adjustment, special levers and locking devices were used, allowing the tension to be adjusted with precision comparable to jewelry work. Roman engineers left behind diagrams and descriptions explaining how to determine the equal elasticity of the beams. By the angle of deflection of the levers, the sound of tension, and even the resistance when turning. The sound of a torsion bar in operation was unique, low and hollow, as if a taut nerve were being released, or a tightly coiled spring were being unwound. The energy stored in the living beams was released in a fraction of a second, instantly accelerating the bolt, arrow, or stone to speeds at which wooden shields cracked and armor was pierced. The torsion principle allowed machines of virtually any size to be created, from small scorpions carried by two soldiers to huge ballistas mounted on towers. The force of the shot was limited only by the strength of the wooden frames and metal bushings. Torsion machines did not lose their lethal force even after long storage, provided they were properly maintained. Engineers carefully monitored the condition of the wires, regularly lubricating the bundles with olive oil so that they would not dry out in the sun and lose their elasticity. In wet weather, the mechanisms were covered with thick leather covers, as moisture was the main enemy of torsion artillery. Wet wires lost their elasticity, and the power of the shot dropped sharply. The effectiveness of this system was so high that the Torsion principle remained virtually unchanged for many centuries. From the Hellenistic states to the late Roman Empire, the Romans brought the technology of torsion to the limit of the physical strength of the materials available in their era. In a sense, their machines were true biological engines, operating according to the laws of mechanics, but made of organic, living materials. Roman engineers understood perfectly well that the force of twisting provides a much sharper, more concentrated impulse than the bending force used in a conventional bow. The projectile achieved maximum acceleration literally in the first moments of flight. This gave it a flat, smooth trajectory and the very sniper accuracy that the Romans' enemies feared so much. But even the most powerful spring is useless if you don't know where the projectile will fly. In the next chapter, you will learn how the Romans used geometry, protractors, and calculations to turn the raw power of torsion into the perfect tool for precision killing. What if I told you that every shot from a Roman ballista was the solution to a complex equation? Roman engineers did not build machines by eye, as is often portrayed in romantic descriptions of antiquity. They used rigorous mathematical formulas based on observation, experience, and clear physical principles. The main secret was a modular calculation system, at the center of which was a single parameter, the diameter of the opening for the torsion beam. All other dimensions of the structure depended on this parameter. All the proportions of the machine were calculated based on this single parameter, which was called the module. It served as a kind of base number, a unit of measurement for the entire structure. The length of the levers, the height of the frame, the diameter of the rods, the power of the arms, the thickness of the bowstring, all of this was a multiple of the diameter of the hole. Engineers knew that if you wanted to throw a stone weighing 30 kilograms, you simply had to substitute the weight of the projectile into the cubic root formula, and you would get the ideal module from which to scale the machine. It was not an intuitive art, but a system based on precise calculations. This discovery made it possible to scale weapons with incredible ease and high repeatability. There was no need to reinvent the machine for a new type of projectile. It was enough to calculate a new module, after which all parts were enlarged or reduced by the same coefficient. This principle effectively turned Roman artillery into a construction set, where each component could be adapted to the conditions of a particular campaign or type of siege. Geometry became the main weapon of the Roman engineer, both in the workshop and on the battlefield. They used complex tables, protractors, and calculations to determine the optimal elevation angle for maximum range or accuracy. An error of a single degree could shift the point of impact by tens of meters, which was critically important when firing at walls or area targets. Therefore, calculations were checked several times, and experienced artillerymen were able to estimate the angle by eye, then check it against the instruments. The Romans understood perfectly well the relationship between the weight of the projectile, the tension force, the density of the strands, the elasticity coefficient, and the final flight range. Special calibration tables were created for each type of machine, indicating the parameters for different distances. This allowed artillerymen to quickly make corrections in combat conditions without long delays. It was a kind of analog of modern ballistic tables, only created 2,000 years earlier. The precision of the parts was essential for the machine to function properly. Templates, measuring rulers, metal gauges, and wooden patterns were used. Any deviation, even a few millimeters, could cause asymmetry, leading to a loss of power or a shift in trajectory. Roman engineering culture had reached such a level that many parts of different ballistae were interchangeable, essentially making them the first standardized artillery systems in history. Mathematics made it possible to calculate not only dimensional proportions, but also the strength of materials. Engineers knew where the wood experienced maximum stress, where dangerous stresses occurred, and how to redistribute the force of impact so that the machine would not break. These areas were reinforced with bronze plates or iron rings. Each ballista became a kind of masterpiece of ancient structural engineering, created many centuries before the science of material strength was formulated. Knowledge of geometry allowed the Romans to fire at invisible targets, troops behind hills, sections of walls hidden by smoke, even ships that were not visible from the artillerymen's position. Observers transmitted coordinates, and calculations set the angles of inclination of the machine using protractors, calculating the height of the arc. This was the first organized firing from covered positions in history, something that centuries later would become the basis of artillery science. Musical instruments were even used to tune the machines, the strings of lyres and kitharas, a tuning fork, or simply the engineer's keen ear. The tensioned wires of the torsion beams had to sound at the same frequency. If both beams sang the same note, it meant that the tension was perfectly balanced. It was an amazing union of physics, music, and engineering, reflecting the precision of the ancient masters. This mathematical harmony transformed the chaos of war into an orderly procedure of destruction. The Romans proved that intelligence, calculation, and control over numbers on the battlefield are stronger than fury and blind courage. If you like it when science defeats brute force, be sure to like this video. Don't forget to subscribe to the channel so you don't miss any new videos. Are you ready for the shocking truth about power that can shatter stone? If the Scorpion was a sniper rifle, then the ballista was the howitzer of the ancient world. These huge machines were designed specifically to break down fortifications and hurl heavy stone projectiles over long distances. Their appearance revolutionized the rules of siege warfare, allowing armies to attack cities without getting close to the walls. The Romans understood that such a tool could give them a huge advantage. Therefore, they paid special attention to the development and use of this machine. The ballista worked on the same torsion principle as the scorpion, but was superior in size and power. Its massive frame needed to be reinforced with iron plates, which helped it withstand the enormous loads when thick ropes were pulled. The iron protected the structure from deformation and extended the service life of the machine. The stronger the ropes, the more powerful the shot, so engineers always sought to use the strongest materials. A winch was required to cock the mechanism, and it had to be turned by several soldiers at once. This process was long and laborious, but the result was worth the effort. Specially treated round stones of various sizes served as projectiles for the ballista. The Romans carefully ensured that the stones were of the right shape, as an uneven stone could fly anywhere, reducing accuracy. Each stone underwent rough processing to meet the required parameters. Workers measured its weight to determine the tension required for firing. This increased the predictability of the projectile's flight and made the ballista a more reliable weapon. This approach allowed the legionnaires to fire accurately and repeatedly. The ballista's impact was so powerful that it could break through the battlements of fortress walls and even destroy sturdy gates. A stone projectile fired at tremendous speed swept away everything in its path. If it hit a dense formation of soldiers, the impact was catastrophic. People fell, shields were shattered, and the horror of such a defeat quickly spread through the ranks of the defenders. For an army standing under the walls, this effect was of great importance. Fear and chaos often brought victory faster than the force of weapons alone. The range of heavy ballistas could reach 500 meters or more if conditions were favorable. This allowed the Romans to fire at enemy fortifications while remaining outside the range of the defenders' throwing machines. From the height of the fortress wall, it was impossible to reach such machines, hidden at a safe distance. The besieged witnessed huge stones methodically striking their walls, and there was nothing they could do about it. This would have broken the morale of even the most steadfast defenders. The city gradually turned into a pile of rubble under the heavy blows of Roman siege engines. Roman engineers created universal machines that allowed them to quickly change the angle of fire. The ballista could be tilted to redirect fire from the upper parts of the wall to the lower parts, where the gates or weak areas of the fortifications were located. This approach gave the besiegers more freedom in choosing their targets. The rotating parts of the structure helped to direct the machine in different directions without having to reposition the entire heavy platform. This saved the soldiers time and energy, as each such maneuver would have required considerable effort. Thanks to this, the Romans were able to react quickly to the actions of the defenders. The ballista was so accurate that it was used to methodically bombard a single point. Stones struck the same spot over and over again, gradually loosening the masonry. Fortress stones that seemed unshakable began to crumble under repeated blows. This required not only the accuracy of the machine, but also the coordination of the crew operating the ballista. Each member of the crew had to understand their task in order to ensure the stability of the firing. Any mistake could reduce the effectiveness of the bombardment or put the machine out of action. There were different modifications of ballistas, each designed for its own tasks. There were light field models that could be quickly moved across the terrain. They did not have the same power as the siege versions, but were useful in combat against moving targets. There were also huge siege versions built to destroy walls and gates. Some machines were mounted on wheels so they could move with the army. This mobility gave the legionnaires a strategic advantage, allowing them to quickly change positions. Ballistas often used incendiary projectiles, which turned ordinary shelling into a fiery spectacle. For this purpose, pots filled with a combustible mixture or stones wrapped in burning tow were used. When these projectiles hit inside the city, they could cause large fires that distracted the defenders from their defenses. The flames quickly spread through wooden buildings, creating chaos and panic. The Romans understood that fire could be as destructive as stone. Therefore, incendiary shots became an important part of their siege tactics. These machines became the pinnacle of ancient engineering and a symbol of the power of the Roman army. They combined precision, power, and reliability, which made them effective weapons for centuries. The Romans knew how to organize production on a huge scale, which allowed them to supply their armies with thousands of identical machines. This approach was unique in the ancient world, where standardization was almost non-existent. But how did they manage to produce so many identical mechanisms? In the next chapter, you will learn the secrets of Roman standardization. The secret of the Roman army's success lay not only in the ingenuity of its design, but also in its ability to mass produce it. The Romans were the first in history to introduce a system of complete standardization of military equipment. Apart from a ballista made in Britain fit perfectly into a machine assembled in Syria. This was achieved thanks to strict state standards and a unified system of measures. All workshops worked according to the same drawings and tables approved in Rome. Engineers in the most remote corners of the empire spoke the same technical language. This unification solved the main problem of logistics and repairs during the war. If a machine broke down, the legionnaires did not need to look for a unique craftsman to repair it. They simply took a spare part from the warehouse or removed it from another damaged machine. The production of siege weapons was divided into specialized stages, reminiscent of modern factories. Some craftsmen were engaged only in forging metal parts, others in woodworking, and still others in preparing the cores. This improved the quality of the products and the speed of their manufacture. Each legion had its own artillery and spare parts. Not only ready-made machines were taken on campaigns, but also blanks for quick assembly of new ones on site. The Roman army carried with it not just weapons, but an entire mobile factory of death. Standardization also applied to ammunition, which was critical for firing accuracy. Stone cannonballs were carved according to strict templates, with a fixed weight and diameter. This allowed artillerymen to use pre-compiled firing tables without additional calculations. Quality control was extremely strict at all stages of production. Those responsible for stamping the product were personally accountable for its reliability. Defects in military production were equated with treason and punished accordingly. Thanks to this system, Rome was able to quickly recover losses in equipment after heavy battles. New machines were supplied to the troops in a continuous stream, ensuring constant superiority in firepower. The industrial power of the empire worked tirelessly for the war effort. Unification made it easy to train new engineers and artillerymen. A soldier transferred from one legion to another would immediately take up a familiar machine and start working. He did not need to retrain or get used to the peculiarities of the local equipment. Standardization turned the art of creating siege engines into a routine technological process. This deprived war of its romanticism, but made it incredibly effective and predictable. Rome won through order and system, against which the barbarians had no chance. Guess who was the most valuable person in the legion, guarded better than the treasury? It was not a general or a heroic centurion, but the optio ballistari, the commander of the artillery crew. His role was so important that the loss of such a person could weaken an entire section of the front. The most sophisticated machines remained mere wooden frames, without people capable of setting them up and operating them. The commander understood every mechanism and knew how to get the most power out of the machine. Therefore, the optio's ability to work under pressure was valued above many military exploits. Training an artilleryman took many years and required a rare combination of precise knowledge and practical experience. Artillerymen needed to understand the basics of mathematics, physics, and mechanics in order to calculate the trajectory of a shot. They were not just soldiers, but the true intellectual elite of the army, capable of thinking quickly and accurately. Such people knew how to read detailed drawings and understand complex mechanical diagrams. They could take geodetic measurements directly in the field, adjusting the position of the machine relative to the target. In addition, they knew how to repair parts in any conditions, even in the midst of a siege. The crew of one machine included a dozen people, each with their own specific task. Some soldiers set the gates in motion by pulling powerful cables to the required level. Others were responsible for preparing and feeding the shell so as not to delay the firing process. The gunners monitored the direction of the barrel and adjusted the angle to achieve maximum accuracy. The commander coordinated the actions of the entire crew and ensured that each stage was performed perfectly. His work resembled that of a conductor who creates harmony from a multitude of precise and rapid movements. The team's coordination was achieved through endless training, during which each action was practiced until it became automatic. Reloading and firing took only a few seconds, which gave the Romans a huge advantage in battle. No one could afford to make a mistake on the battlefield, because any delay put the entire team at risk. The soldiers understood each other without words and acted on prearranged signals. Commands were given with short gestures or sharp whistles that could be heard even in the noise of battle. This level of training turned the unit into a single organism. Artillerymen had to be able to determine the distance to the target with just a glance. Even a small error in estimating the distance could negate complex calculations and render the shot useless. The ability to sense distance came only with experience, which was passed on from veterans to newcomers. This took place right at the machine, where young soldiers learned to listen to the advice of their elders. A mistake was not just unpleasant, it could affect the outcome of the battle. Therefore, every artilleryman strove to develop this most important ability. Particular attention was paid to the condition of the machine itself, because the slightest malfunction could lead to tragedy. A broken torsion bar could maim or kill soldiers standing nearby, which made the work dangerous. Checking the cables, frames, and all fastenings was a daily ritual that was given almost sacred significance. The team carefully inspected each element to ensure its functionality. Any crack or weakness could cause a disaster at the most inopportune moment. Therefore, discipline in the care of the ballista was stricter than anywhere else. The engineering corps enjoyed privileges that emphasized its importance to the army. Artillerymen received higher salaries, which motivated them to improve their skills. They were exempt from the heavy camp work performed by the regular infantry. The Romans understood that the professional knowledge of an engineer was a strategic resource that needed to be protected. Training such specialists was long and expensive, so they tried to protect them from unnecessary burdens. The state valued people who were able to maintain the combat readiness of heavy machinery. In battle, artillerymen became one of the main targets for the enemy. The enemies understood that by destroying the crew, they would not only kill several soldiers, but also put the entire machine out of action. Ballistas always attracted the enemy's attention because of their destructive power, so the enemy sought to neutralize them as quickly as possible. To protect the crew, the Romans placed units of archers and heavy infantry nearby. These units provided cover, allowing the artillerymen to work without constant threat. But even such protection did not always save them from danger. It was these people who turned complex calculations into real destruction of fortresses and enemy structures. The artillerymen had to keep a cool head even under a hail of arrows and stones. A steady hand and accurate calculations often decided the outcome of sieges and field battles, where every minute counted. The machine itself was only a tool that remained useless without an experienced operator. The real weapon was the person who knew how to make the mechanism work with maximum force. That is why the role of artillerymen was so important. But even these geniuses of war had a weapon that they called a wild donkey because of its untamed temper. This machine was unpredictable and could even harm its operators if used incorrectly. Many artillerymen treated it with respect and caution, understanding its nature. Despite the danger, this machine remained an important part of the Roman arsenal. In the next chapter, you will learn why one of the Roman machines was dangerous even to its creators. The Onager was the simplest, but at the same time the most destructive type of Roman siege equipment. Unlike the two-armed ballista, it had only one lever, which was driven by a powerful torsion bar. The machine got its name, meaning wild donkey, from its strong recoil, reminiscent of a kick with a hoof. This machine was designed exclusively for firing heavy stones and incendiary projectiles. The Onager could not boast the sniper accuracy of the ballista, but it made up for it with its brute force. A stone weighing 50 or more kilograms, launched in a high arc, fell on the roofs of houses and the heads of defenders with terrifying force. The main part of the Onager was a sling attached to the end of the throwing lever. It extended the lever at the moment of launch, significantly increasing the initial velocity of the projectile. It was the use of a sling rather than a spoon-shaped holder that was the secret to this machine's long range. The impact of the lever against the stop beam when fired was so strong that it shook the entire structure. Therefore, Onagers were often placed on special platforms made of turf or clay to dampen the vibration. Without this cushion, the machine could fall apart after a few dozen shots. Loading the Onager required enormous physical effort and the use of large gates. The lever was pulled to the ground, overcoming the resistance of a thick bundle of tendons. At that moment, the machine resembled a predator ready to pounce, full of restrained fury. Onagers were often used to throw not only stones into the city, but also animal carcasses or prisoners. This was an early manifestation of biological warfare aimed at spreading disease. It also had a powerful demoralizing effect on the inhabitants. Despite its power, the Onager was dangerous for its own crew. A broken sling or stopper could cause the stone to fall directly on the heads of the artillerymen. The courage of the people who worked with these monsters commanded respect even from hardened legionnaires. The simplicity of the design allowed onagers to be built directly at the site of the siege from available wood. This made them the ideal choice for quickly organizing the bombardment of a fortress. While complex ballistas were being transported in a convoy, onagers were already beginning to destroy walls. The sound of an onager firing and the whistle of a flying stone were music of destruction for the Romans and a funeral dirge for their enemies. The fall of a huge boulder from the sky was impossible to predict and impossible to stop. It was divine punishment, created by human hands. The onager became a symbol of the inevitability of Roman retribution, wiping cities off the face of the earth. It knew no mercy and chose no targets, destroying everything that fell within its range. It was the weapon of total destruction of the ancient era. The Romans did not just throw stones, they created high-tech projectiles that were ahead of their time. Special bolts with iron tips in the shape of a pyramid were used for ballistas and scorpions. This shape provided incredible penetrating power, allowing them to pierce shields and armor. The bolt shaft was made of hard wood and carefully balanced. The fletching was made of wood or leather, not feathers, as in ordinary arrows. The rigid fletching ensured flight stability at the supersonic speeds reached by the projectiles. Stone balls for ballistas were not just round cobblestones. Stonecutters gave them a perfect spherical shape to improve aerodynamics. The smooth surface reduced air resistance and increased flight range and accuracy. There were also lead projectiles which, despite their small size, possessed enormous kinetic energy. A small lead ball fired from a powerful machine acted like a modern bullet. When it hit a person, it caused terrible internal damage. The Romans experimented with the shape of projectiles, creating stones with notches or holes. In flight, such projectiles emitted a terrifying whistle or howl, striking fear into the enemy. The psychological attack began even before the stone touched the ground. Hollow clay vessels filled with oil or a mixture of sulfur and resin were used to set buildings on fire. Upon impact, the vessel would break, and the liquid would instantly ignite, creating a fire that was difficult to extinguish. These incendiary bombs were a nightmare for the wooden fortifications of the barbarians. An interesting invention was the chain shot for destroying enemy ships' rigging or dense infantry formations. Two cannonballs connected by a chain spun in flight, sweeping away everything in their path. It was a weapon of indiscriminate action that caused massive damage. The calibration of the shells was extremely strict. Any cannonball that did not fit the template was rejected. The use of a non-standard shell could damage the expensive machine or lead to an unpredictable shot. The logistics of supplying ammunition were as important as supplying food. Archaeologists find thousands of such processed stones at ancient siege sites, which indicates the scale of their use. These were not single shots, but a real artillery barrage. The shell manufacturing industry worked tirelessly. The attention to detail, even in something as simple as the shape of a stone, shows the perfectionism of the Roman military approach. There are no small details in war, and every gram of weight and every millimeter of surface area mattered. It was this attention to detail that made Roman artillery the best in the world. Imagine a machine gun created 2,000 years before the invention of gunpowder. Roman engineers did not stop at single shots and created the polybolus and an automatic ballista. This marvel of technology could fire continuously as long as there were arrows in the magazine. The invention is attributed to the Greek engineer Dionysius, but it was the Romans who perfected it. The arrow-feeding mechanism worked by rotating gates connected by a chain drive. A single movement of the lever simultaneously pulled the bowstring and fed a new bolt from the magazine. The uniqueness of the polybolus lay in the use of a chain drive and gear wheels. It was one of the most complex mechanisms of antiquity, requiring the highest precision in manufacturing. The gears had to fit together perfectly so that the machine would not jam. The rate of fire of such a machine was fantastic for its time. It could fire arrow after arrow at intervals of a few seconds without requiring a long reload. One polyball could replace an entire squad of archers, creating continuous dense fire. The main advantage was that the gunner did not have to aim each time. The machine remained aimed at a single point, and all the arrows flew at the same target. This was ideal for defending narrow passages or gates. However, the complexity of the design was also its main drawback. In field conditions, amid mud and dust, the delicate mechanism often malfunctioned. The polybow required skilled maintenance and thorough cleaning, which was not always possible in battle. Therefore, polyboli were mainly used as stationary weapons in fortresses or on ships. There, in relatively clean conditions, they could show their full effectiveness. It was a weapon for special tasks, not for mass use. Nevertheless, the very fact of the existence of such a machine speaks to the level of technological development in Rome. They were on the verge of an industrial revolution using the principles of automation. All they lacked were more advanced materials and a source of energy. The polybol went down in history as a demonstration of engineering audacity and an attempt to mechanize the process of killing. It was a technical masterpiece centuries ahead of its time. Its blueprints still inspire admiration among modern designers. The Romans proved that there are no limits to the perfection of weapons. But unfortunately, even the most ingenious technologies cannot save an empire if it is collapsing from within. In the last chapter, we will talk about how this knowledge was lost. Roman artillery was the pinnacle of ancient engineering, but with the fall of the empire, this knowledge was lost. Complex mathematical calculations, manufacturing standards, and secrets of wire processing were forgotten for 1,000 years. The Middle Ages faced war with much more primitive technologies. The main reason for this loss was the destruction of the state system of education and production. Without centralized control and funding, it became impossible to maintain complex machines. The barbarians who captured Rome did not understand mathematics and did not know how to operate ballistas. The secrets of torsion machines were passed down from generation to generation within a small circle of craftsmen. When this chain was broken by wars and epidemics, there was no one left to restore the technology. Books and drawings were burned in library fires or rotted away in damp basements. The highly accurate Roman artillery was replaced by cumbersome and inaccurate trebuchets with counterweights. They worked on the principle of gravity, which was simpler and easier to understand for medieval craftsmen. The art of sniping with huge arrows was replaced by simply throwing stones. It took Europe centuries to get back to the level of Roman standardization. It wasn't until the Renaissance that engineers started rediscovering the laws of ballistics and mechanics. Leonardo da Vinci studied descriptions of Roman machines with admiration, trying to recreate them. The loss of Roman technology is a tragic lesson in how fragile the progress of civilization is. Knowledge accumulated over centuries can disappear in a couple of generations of chaos and ignorance. The history of Roman artillery reminds us that technological superiority does not guarantee eternal existence. We still find parts of ballistae and stone projectiles that silently bear witness to past greatness. These artifacts tell the story of an empire that believed in the power of reason and order, an empire that turned warfare into an exact science. Roman siege engines remain an unmatched example of engineering elegance and efficiency. They proved that with the help of mathematics and wood, it was possible to create weapons of terrifying power. This legacy continues to inspire engineers and historians around the world. Today, we can only simulate the operation of these machines on computers, marveling at their characteristics. They were perfect for their time and their tasks. And who knows what other secrets are hidden in the undiscovered drawings of Roman engineers. Rome fell, but the glory of its weapons has survived for millennia, remaining the benchmark of military power. The history of Roman siege engines is not just a story about war, it is a story about human genius that finds application even in destruction. We have seen how mathematics, physics, and standardization created weapons that were unparalleled in the ancient world. The Romans showed that precision and discipline beat brute force and numerical superiority. Their legacy teaches us that true power lies not in muscles, but in knowledge and organization. Ballistas and scorpions were just the tip of the iceberg of a huge, well-oiled system called the Roman Empire. And although these machines have long since crumbled to dust, the principles laid down by their creators live on in modern engineering. What impressed you most about Roman artillery? The mathematical precision of the calculations or the brutal effectiveness of the scorpions? Write in the comments what other ancient technologies you would like to learn about in future episodes. And be sure to subscribe to the channel so you don't miss out on new journeys into the past.